Welcome everyone to the system seminar. Today I'm very happy that Kaan Onarlioglu is giving us the honor to talk about his work, some of his work that he's currently doing at Akamai. We've known each other for 1.5 decades or so. 2 decades?
Almost, yeah.
For a while. You're doing awesome work at Akamai, web stuff. So if you have any questions during his presentation, raise your hand, and Kaan said that he's willing to entertain your questions during the seminar as well, so you don't have to wait until the end. Yeah, and with all that said, please tell us why the internet is doing.
All right, let's do it. So the audio is fine, video is fine, perfect, let's go. I'll keep looking at that screen, so sorry about that. I don't have the slides in front of me because I'm Mac challenged. I'll figure it out. So yes, I work at Akamai. I'm a principal architect. That means I don't write a single line of code, right? So my job is looking at diagrams and making decisions, especially security decisions about those things. And this talk is going to be about some of those big problems that we've been dealing with for the past 10 years or so. They're really big problems. They're unresolved problems. They're not going to be resolved anytime soon. That's why the internet is doomed, right? I'm also part-time faculty at Northeastern University, so my official task is teaching. So, I'm not a research professor, but it's charity work. I do a lot of research with the talks at Northeastern as well. So I'm going to reference some of the papers that we did there, just to give you, some references in case you're interested in learning more. That being said, this is not a paper talk. Right? This is going to be a very quick overview of a lot of different things. I'm going to show you a lot of examples. I know, this is not strictly a security crowd, so no background assumed. I'm going to show you very specific examples, completely unscientific examples, more like examples you would see at a black hat talk. But the really important thing is the final message. So wait for the final 5 minutes of this talk. That is going to give you the perspective that I want to convey here, okay? So yeah, hopefully you're in the mood for a TED Talk. So do me a favor, can I see a raise of hands if you saw this talk? Okay, not a lot of people, that means I'm not able to skip the background. Perfect, that's how I like it. All right, so can I get rid of this maybe? All right, perfect. Right. So, if you're into security, if you're following the security media, you may see a lot of news like this. Oh, for the record, everything's public information. Okay, I'm not going to ask you to fill out an NDA. So, all of this is public. You may see news like this where it says Akamai wrestles with cache problem this, cache problem that, and you're going to see this very often. Okay? So this is old, but just Google for it. You're going to see a lot of different things that look like this every other month. And then when you see a cache problem, you can also, bet money on the spot that I'm going to be interviewed. I'm going to be involved in some way. And if you look at my statement, it's going to be a very, mild statement saying something like, Akamai takes this very seriously and we're going to fix this particular issue. That being said, this happens for a lot of valid reasons, and we don't promise to fix it if something like this happens again next week, right? You can, and you will see a lot of new instances of these attacks. There's nothing we can do about it. And of course, I can't go into a lot of detail in these public statements, but we'll see hopefully at the end of this talk why that's the case. And then, here's another one from last year or 2 years ago. I don't quite remember. And it names Akamai an F5, right? So it is research. It's about a vulnerability. The researcher said that they were able to exploit if Akamai is paired with F5 in some web architectures. And this actually made it to a top 10 web hacking techniques list. So this list is not an arbitrary list. It's legit. It's published, created by Proxied and James Kettle. So these are the people behind, Proxied is behind the burp set. So the industry standard penetration testing tool for web applications. And James Kettle is a researcher himself that contributes a lot to the security field. So legit list, if you make this list, you're legit, okay? And then, if you read it, it says, okay, so this research is awesome. And then both vulnerable server vendors, Akamai and F5, they refused to pay bounties. And then they made their customers pay bounties instead. So they're terrible, right? So best not to think about it. You see something like this, it's pretty damning, right? So you don't want to be in the news with a description attached to it like that. But here's the thing that the world didn't quite know back in the day. Akamai had nothing to do with vulnerability. It wasn't our fault. We were not contributing to it. But of course, we didn't say that publicly because we didn't. The research itself is really good research. It's very detailed. Yes.
To be fair, isn't that what every vendor always says when faced with a vulnerability?
What do you mean?
It's not our fault. We didn't do it. It's someone else's issue. This
Well,
is like standard industry
but
response. To...
maybe they do, but this is not like I'm not a PR person. As an engineer and architect, I'm telling you the facts. We were really not involved. But we couldn't say that publicly because we didn't want to come across as trying to minimize the researchers' work or to disparage them because the research is valid. It's just that Akamai is not. So they were attributing the vulnerability to Akamai for other reasons. Okay. So this is the second question then. Why does this happen? This happens all the time too. You see Akamai in the news attached to name attached to a vulnerability, but Akamai played no part in it. So how come? And then this is from a review I got a couple of weeks ago from a top conference in our field. It was a paper about an attack called HTTP request smuggling. And then this reviewer said that I'm not convinced that this is a real attack. At the same time, same day, 2 hours before I received this review, we declared an incident at Akamai because about 100 top customers of ours could potentially be impacted by a new flavor of this attack. Right, so the entire company was in fire drill mode trying to fix this. How many hundreds of thousands of dollars wasted on that incident efforts, I couldn't even tell you. And yet this reviewer just said that this is not a real thing. I made a LinkedIn post about this, which you're not supposed to do. You're not supposed to post reviews, of course, but I did because I was really frustrated and it's my most viewed and most liked posts ever. So yeah, then the final question, why does this happen? No, it is a huge thing, and yet, why does an academic reviewer think that this is not real? All right, so quick background, okay? So, if you look at any textbook, you're gonna see that this is the, client-server model, right? So web applications work like this. Client talks to the web server, they get something done together over HTTP, of course, right? That means that this is a lie. This never happened in production environments. It's only for a student project and bedroom project. In real life, you always have a proxy in between. Again, I promise you. Okay, without proxies, there's no internet. And then the proxy could do a lot of different things. It intercepts traffic, obviously, and then it can do a lot of different things. It can reroute traffic. Maybe it's a load balancer. It can filter traffic. Maybe it's a web application firewall trying to catch attacks. It could do caching, right? So maybe it's just something to improve the performance of the system. And many other things. Anything you can imagine, it can do. It's a web server itself, right? It speaks HTTP, so it's a web server in essence. And then that box, this is still a model. In fact, that box can be a lot of different boxes. And again, in real life production systems, again, I promise you it's going to be n different proxies chained back to back doing different things. And one of those things, one of those applications could look like this. It could be a CDN, a content delivery network, right? So a CDN is a global internet overlay of a cloud platform of these proxies doing all sorts of stuff, right? So they started out as performance improvements for the, highly scalable internet applications. But today, you can put any application on those edge servers. So you can carry traffic and then also apply some application firewall features on it. And then, load balancing and this and that. Again, edge computing, and you can run workloads on those machines and do any computation you want. So it's very flexible, okay? So some terminology for you. This one, we call the origin server because it's where the content originates from, this authoritative source of the content. The CDN doesn't store anything. It doesn't host anything, let's put it that way. The CDN can cache content, but it's temporary. And then, of course, the origins pay to benefit from the CDN services, right? So this could be your favorite bank, for example, paying millions of dollars to Akamai. And then the end users are just us in front of our browsers interacting with the website. We get the benefits for free. Right. So this is some arbitrary, yes, go ahead.
There's typically also a client proxy. Client is one, right? You have proxy on the server, and you have also typically a proxy on the client side.
So yes, you can have on client proxies, on client.
Client systems, like BU has its own.
So yes, so this is a CDN, but you can chain multiple things into this picture, right? You can have on-prem proxies, and then a CDN, and then maybe another CDN, and then maybe another 5 different proxies. It's going to be a lot of things changed back to back.
Just not all of them are controlled by the server environment. Some of them.
No, it could be different parties, and that's going to be very important in a moment. Right. And then this is some arbitrary, completely non-scientific data. I don't know where they get their data from, but it's the only data source that's publicly, gets close enough to my internal knowledge that I can reveal to you. But take any arbitrarily large popular slice of websites, top 10K, 100K, 1 million, you are going to be seeing CDNs deployed in about 50 to 70% of those real production level busy websites. Okay, I'm showing you this because after showing you what I'm going to show you next, you can say that well, CDNs are trouble, but proxies in general are trouble. Let's get rid of them. Well, you can't. It happens for a reason. So CDNs and proxies are considered critical infrastructure in some parts of the world, literally in Germany, for example, right? Because they have an existential place. You take the CDN out of the picture, you cause a lot of problems for everybody on the internet. Yes.
Most of the time, it's also CDN's network that bear the brunt of the denial of service attacks, distributed services. So ideally, if I host something by myself and it's public, it's going to be down most of the time, right?
Exactly. So that's exactly the problem, right? So that's why sometimes you see some news like this. Thankfully, it happens very rarely. But a CDN goes down, and then it takes, according to the news, it takes half of the internet down with it, and then you can think, well, so the official numbers for Akamai, for example, say that Akamai influences or carries about 30 to 35% of the planet's traffic. But why does more than 30% go down? Well, that's exactly why. You take the CDN out of the picture, that traffic needs to be handled elsewhere, and that's going to just figuratively fry also all of the internet's backbone networks and everything else. Right, so the impact is the blast radius is way beyond Akamai's customers in that case. And so it's all to motivate that this is critical infrastructure, and it is an existential place. You can't remove CDNs. We don't have internet without CDNs. Okay? All right. So starting this moment, I'm going to show you 3, maybe if we have time, 4 case studies. Again, I promise you it's not going to be paper talk. It's not going to be research flavored. It's going to be very specific attacks. There are general versions of this, but I'm not going to spend time trying to explain that generalization because I really want everybody with or without security background to appreciate what's happening here. Right? So it may look like simple hacking tricks, but they're not. All right. So I said proxies and CDNs can cache content, right? But how do they decide what to cache and what not to cache? Well, HTTP offers one and only one mechanism to do that. It's called the cache control response header. So an origin server can respond with a header that indicates to all the downstream proxies whether the content, whether the response is cacheable or not. Okay. And then this is great, but then think about it. You have a huge cloud platform, right? You're an old school technology company. You have who knows how many web applications distributed all over the planet. And one day you decide to change your cache policies. Well, you need to first identify all the assets that are going to be impacted. Then you need to contact the owners of the machines, the admins of those machines, and then file a change management ticket. And in real production size, again, a change management ticket can take upwards of 6 months to get processed because of change safety reasons. So bottom line, making changes is next to impossible in real life using cache control headers. And because of that, again, you'll need to take my word for it. Big production websites never ever use this. Right? Instead, there's a more convenient method. They can go to their proxy or CDN vendors portal. Right? With Akamai, you can go to control.akamai.com. There's a nice web interface. In that interface, you're going to see a checkbox that says, ignore cache control headers. Right? Just drop them. Don't look at them. And you do that, and then right next to it, there's going to be a centralized interface where you can neatly configure your caching rules with that interface. Right? So you define a rule there. You hit enter. In 2 minutes, it applies to all of your web properties. Easy. So this is the way it's done. And this is the only way it can be done with huge platforms. The other option is simply not feasible. Okay. And then these caching rules can be as narrowly and specifically prescribed as using regular expressions on every single part of a request, or it could be as general as cache everything that is a static file extension. Okay, there's a request for something dot style sheet. All style sheets are supposed to be non-sensitive and they're supposed to be static, so cache all of that. You can create these wildcard caching rules. You'll need to take my word for it. These general rules are applied everywhere in production environments because usually the people configuring these caches are not the same people managing the web application, so they don't know what needs to be cached, so they make these very general decisions. Yes.
Question: where is the caching taking place on the CDN boxes or on the client's side?
The caching is done on these machines in the CDN.
On these machines. Okay.
All right, so here's the problem. So this is a URL, everybody knows what this is. And then this is the same URL. Exact same information represented in a slightly different way. Right? So, this is called a clean URL. It's just tidying up this representation a bit and making it look, making it shorter and cleaner. That's why it's called clean URL. So let's see why this actually needs to happen in practice. So you look at a URL like this, you assume that there's a server root directory, and under that there's a home directory, and under that there's an index.html, right? You click on this thing, you expect to get that HTML back. Well, that's in your imagination. That's fantasy. That doesn't need to happen, right? That's just a string, and the server is free to interpret that in any way it wants. But we, like to use file system metaphors because it's easy to understand for humans. Well, they said, well, let's design a new representation where we get rid of that file system metaphor. Right? Now, there are no files, no directories, no file extensions. This is just an endpoint. And these are path parameters, path components, let's say, that could map to any endpoint, up to the server to interpret that. Right? And then they said, while at it, let's simplify this query string as well. So previously we had the parameter names and values and all this fancy syntax. They said, let's get rid of all of that, make it shorter. Let's include our parameters as path parameters as well. And we don't need the names, right? I don't need to know that it's called lang. I can infer that from the order. So let's get rid of all of that and clean up our representation. But these are equivalent to a server that knows how to parse and interpret that. You're going to see clean URLs used all the time. I'm sure you've interacted with websites that use that, and it is more or less the standard in RESTful APIs and other API applications. Practice. Yeah.
Never seen the REST APIs.
So again, who use?
I don't know how to respond to that. It's very. You can still use query strings together with them, but you typically don't interact with file extensions, right? It's an API. There's no files to use.
So again, who is generating this URL, clean URL? Where is it going?
So
is it the client that is when it's going on the browsing, or is it the server when sending that information to your proxy, well, not clear where.
So the website developers and then the server operators together decide on this representation, right? And then your browser or your API client interacts with the service, of course. So you make requests to these endpoints, but then it's up to the application what URLs they expose and how they interpret those. So it's everything.
This is client face. Client sees this.
Okay.
Does it tend to be the case that they just accept both? Like, is it?
Could be. Why not? So it's up to you, right? You're the developer. You get this string.
No, I mean in
Okay.
general, like, is it the case on? Like, I mean, in industry. Like,
It is the case, and it's not ideal, and it's going to lead to a problem in a moment. Okay, so here's the question: you see something like this completely, out of context, right? There's zero context. You get this in an email. Would you click on it? Right? I mean, you probably wouldn't, but still, look at this. It looks like a picture. There's no reason to think otherwise. It doesn't look like your typical attack link. There's no encoded characters that look fishy. There's no JavaScript. You don't see anything fishy in that. But here's the thing: is the client, you are not the server, you're the client. You look at this thing, you have no idea how the server is going to interpret that. It could be really something like this, where there's a picture under this directory tree. Or it could be something like this. You're in fact getting an indexed HTML, and that image and pic.jpg were just parameters, and there is no way you can tell. So here's what happens. This is, let's say, a legitimate bank with a legitimate account.php endpoint page that has your credit card details or this sensitive stuff, okay? And then this is an attack. Okay? You click on this, you don't notice anything going wrong, but you just lost your credit card details. Real attack. So how does it happen? Here's what happens. You have a proxied environment, right? So the web server is the bank. Cache could be any caching proxy. Could be a CDN, could be a standalone proxy, doesn't matter. And the victim gets to, the attacker makes the victim click on something like this. Okay? And then I just replaced the Pokemon part with non-existent.jpg. The important part is it should not exist. And then the cache sees this request and it looks at this cache, says, I don't have anything like this. I can only forward this to the origin. There's nothing else I can do. So it does that. And then the server sees this and the server knows that this doesn't exist. And then it can do one of two things here. It can return a 404, or it could rewrite that request and reroute to that endpoint. Why? Why would that happen? I'm pretty sure you experienced this yourself when you typo something at the end of a URL. Sometimes the server just gets rid of that and serves to the valid part. And some people think that this is for usability reasons, right? You don't get an error page, but you get something in your browser at least. That's not necessarily the case. Here's what's happening. The server looks at that. It says that it doesn't exist, but maybe the client meant this. Maybe that non-existent part was a parameter. So why does this happen? Could be due to many reasons. Could be misconfiguration on the server. Could be something that comes as default in the underlying web application framework. So maybe the web developers didn't even realize that could happen. It could be due to a lot of reasons, but if it happens, then you have a problem because the server is going to respond to the account details. Well, the cache doesn't know. The only thing available to the cache, only piece of information telling what the content could possibly be was in the request, and it was the URL, right? In the response doesn't repeat what content it served. There's no field like that in HTTP. So from the cache's perspective, it was expecting a JPEG. Now the bank does something right here. It actually responds with a cache control. Don't store this. I did something bad that you don't need to know about, but just don't cache this response. But I mean, guess what? What did I tell you? Nobody looks at those headers. And this for a valid reason, for a legit reason. That's the only way to feasibly implement a huge distributed application. And then if this cache happens to have a very general rule, something like, cache anything that looks like a JPEG, now your account details are in cache. All right. So you have a problem now. The attacker can simply request the exact same URL and get your details from the cache. You just lost your sensitive information. Bad. Yes.
This is a very time sensitive attack, right?
It is not time sensitive. Why do you say that?
Because if suppose there is a lot of people using the correct link, right?
Yeah.
The attacker was like, until that file does not get overridden on the cache, then anybody can access my account. Right?
So here's what you would do. That's why we include this non-existent part. You can make this random. You can make this a random thing that only the attacker knows, and you can spam different people with different non-existent.
Because the response is related to the request, right? So
Yes.
you're not caching that under account.php.
No, absolutely. You're caching this thing under this URL.
Okay, so then only somebody who knows that non-valid URL can get that data. I see.
You need the credentials also to be cached. We're not following.
No, so the victim needs to be authenticated already. Of course, they need to be able to
Right.
access the thing, but once
they have an
the
OAuth.
content is cached, it's cached for everybody. Right, so web caches are for public and static contents.
Right.
They're not for caching things behind authentication gates because that doesn't make sense.
Right. So then I don't understand this attack. So where's the attacker here? The attacker sitting on the web cache?
The attacker is just sending the victim through some social engineering means this
Yeah.
link. This link.
Okay. And where is it? What's the threat vector?
The threat vector is if the victim clicks on this link, or they can be somehow their browser tricked into firing a request to that endpoint.
Yeah.
At that point, the caching happens. So the attacker is just a normal person with a web browser accessing this exact same URL here from their home.
So the attacker is a remote attacker somewhere else, just accessing the same.
Same link, exactly.
Okay, and you're saying that the web cache is stupid enough to cache the content without any concern for the current authentication.
So exactly, because the caching rule says that cache everything that looks like a static file, right? So if there's a content and object behind an authentication gate,
Yeah.
that often implies that that content is either not supposed to be public or that content could be dynamic, or both of them, right? So caches are, of course, not for, because it doesn't make sense to cache that. Caching is for public content. And here the assumption is that, the web developers and the operators of that cache, people that configure the cache made is that anything that has a .jpeg extension is public. It's probably my bank's logo, right? It cannot be your bank account details because that would not be in a JPEG. So typically with CDNs, you would have a convenience option that says cache everything that looks like a static file. And in that list, there's going to be all the image formats, all the video formats, JavaScript, CSS, all those things that typically don't contain sensitive information.
So this is an obvious misconfiguration.
It is an obvious misconfiguration, but by whom and why exactly does this happen? So I'm not going to answer that question right now, but a bit later. Yeah, so thanks for all these great questions, and this is a great segue into I guess the next part of the talk. So yeah, these are the questions that I wanted people to ask because the answers are going to be very relevant to these questions. All right. So I made a lot of assumptions here, right? You can say that, hey Kaan, you said that caches need to be configured that way, cache control headers need to be ignored, this and that. How often does this happen? Is this really a real thing? And then, so good question. We tried. So the attack has a name. It's called web cache deception. And then we measured this. And then we found that on a small number of, but very popular small number of websites, we saw that about 10% was impacted. And then we later did a bigger study, and we still saw slightly over 10% impacted by this. Here's the funny thing. The methodology, the crawler, everything's public. Try it at home. You cache things, you report out. We reported everything to the impacted parties. Of course, they fixed it. You do it 3 months later, you get a different 10% impacted. So the same thing keeps happening over and over and over and over again, even though people are aware of this attack now.
One more thing, this only works if you don't have any kind of credential in the URL. You don't have any OAuth token or something.
That's correct. That's correct. I mean, which
Is that
you don't
common?
at that point, yeah. So the assumption is the victim needs to be authenticated and well past all of these, authentication and authority flaws with anything, including
And using some sort of put method or something for exchanging, for maintaining flow information.
Sure. I mean, but that's how we interact with typical web applications, right? I don't know, log into, I don't want to give you names here, but your favorite bank is exactly the kind of link you would click to see the dashboard, right?
Sure, but in order for the backend server to be able to correlate you with subsequent requests, right, there needs to be some sort of flow management.
It's probably in the cookie at that point, right?
Well, so if you're, okay, so but then you need that cookie in order to be able to access the.
You don't, so as the attacker, you don't need anything. The victim needs all of that, the credentials to access, of course. And once they do that access, which
So you're
there's
assuming
a
you
lot
know
to do.
when they access it with fine enough grain that you can get it before anyone else overwrites the same cache.
It is not going to be the same cache because you are supposed to replace this final part, the unique
Oh,
token.
I see.
Yeah.
You put it on this.
Doesn't web browsers usually have CORS headers or something like that that stop you sending requests that are to random websites? So how are you making I think the social engineering aspect of it is also critical. How are you making the other person click this and then make use of the cookies?
That's a valid question, right? I skipped that part. I just assumed that social engineering, we know it happens, and I skipped over all of those details. Yeah, that part needs to happen.
Yeah, because that is critical.
Otherwise, you need to find some sort of CSRF attack, which may not always be viable with modern applications. True.
Send an email.
Super fast. So what the attacker gets is a copy of the page that the user would see. So suppose I'm looking at my banking statement with my details. The attacker gets the same page, but he cannot interact with it. He just
That's correct.
look at it,
Exactly.
right?
You just get a static copy of that page. You cannot interact with that. So so look it up. Just Google it. Two very popular public examples. It happened with PayPal. So you just visit PayPal. Just visit PayPal.com, and you would get somebody else's profile in front of you. It happened with ChatGPT. Again, you visit, you see somebody else's history. Yep.
I want to be super clear. I understand here. The actual domain that's in the URL that you get there is totally legitimate.
That's
If
correct.
I am going to myfavoritebank.com, it says, and I can use the URL inspector to see that it's going to myfavoritebank.com.
Absolutely.
Right. So the social engineering is not as big a hurdle as you might think, because that URL looks legit. It's only this token at the end, which is not unreasonable because you see random you encoded 64 stuff or you encoded 64 stuff at the end of that all the time.
So real life example, people post in support forums. Right?
Yeah.
How they do this thing, somebody says, click on this thing, it's going to get you to the settings page. And it could indeed be, website /settings/ non-existent.jpg. Okay. Oh, there's a lot of questions, so I'll probably only do 2 case studies, not 3. Don't have enough time left. Cool. Right, so that was web cache deception, and I'm going to talk more about this picture at the very end, but for the moment, please appreciate 2 things, and remember this. This happens because of a lot of different things going wrong all at the same time, right? The stars had to align for the attacker, or inversely, everything had to go wrong for the victim, right? A lot of different things. And then it also happened due to an interaction, a bad interaction between 2 different parties, right? So these are not necessarily the same companies, they're not the same technology. Something this happens between 2 different vendors, maybe. And finally, a lot of factors contribute to this, but one of the biggest factors here is a confusion between what these different parties think is the real URL that they're processing. Right? The cache thought that it was working with this URL or that path, and then the bank thought it was this path. Right? So there's a disagreement on the URL or the path. All right, remember that. Moving on to the second case very quickly. Right, another proxy thread architecture, and then this is just a normal request, nothing fancy about it. Well, I'm going to add to this a custom header, right? HTTP supports custom headers. You can include whatever header you want there. If it's not defined in the standard, that makes the custom header. And the specification says that if you're a proxy and if you see a custom header, and if you don't know what to do with it, keep it intact, forward it to the next hop because maybe the next hop knows what to do with it. Okay. And so that's exactly what would happen. This would get forwarded. And then I'm going to add another one here. But this one's different. This one's different because of that question mark. So in headers, the single quote is fine, dash fine, exclamation mark fine, question mark not fine. If you include that, the correct answer, the correct response is returning a 400, hey, the client, you messed up, bad request. Why? Because the RFC says so. It says these are allowed and nothing else. And question mark happens to be inside the delimiter set. Okay. Here's the thing. You know, in the olden days, Akamai didn't actually honor that specification. It wasn't strictly compliant, and it said that your question mark is fine. We'll forward the question mark that header just like any other custom header. Why is that a bug? It actually wasn't a bug. It was non-compliance, but it was there for a necessary reason. We had a lot of customers that had legacy applications and bad clients and buggy clients and this and that. They needed this feature. They used custom headers with invalid characters. They wanted this to happen. And I bet you also want this to happen because otherwise tomorrow nobody's accessing their bags. Okay, so it is a necessary compromise, and it didn't cause any problems for a very, very long time until one day somebody out there noticed that if you combine Akamai with AWS and specifically S3 buckets, their storage service, you have a big problem. So here is what the attack payload looks like. You include these two headers. So let's say this is again our good bank, legitimate bank, and this is the legitimate S3 bucket they use to serve some content. Right? Chaining Akamai into AWS is a very common pattern. And then the attacker includes this. Right? So this, there's no social engineering here. The attacker is sending this request themselves. Okay? So Akamai sees this. Akamai is smart, so they know this is not host. This is question mark host, which is a custom header. We don't know what it is, so it doesn't touch it, keeps it intact, which is wrong, right? It should have blocked the request here, but it doesn't. But at least it goes to the correct endpoint. Right? It includes this host header and forwards the request to this. Now, S3 does something different. S3 looks at this and says, well, this is close enough. Let's get rid of the question mark. Right? Input sanitization. Big security issue. Input should never be sanitized. You'll see a lot of conflicting information online. They mean input validation. If the input is not valid, you don't touch it. If you touch it, you can cause vulnerabilities like this. What's going to happen is, at this point, AWS had another quirk where they honored the first one and ignored the second one. Yes.
But to be fair, they're actually following the standard. They're actually correct in that they should not be getting any question marks in the header. So
I mean,
when you're off standard, everything should be acceptable, right? So
exactly.
people
So
who are violating the standard are the ones who are to blame.
So just to be clear, I'm not pointing fingers or blaming anybody, and this is going to be an important part of my final message. Again, Akamai did something that's non-compliant, and AWS after that also did something bad, and together combined those two badness result in something.
I don't think they did anything bad. They
If you
assume
see a
based on
question mark, you should return a 400.
Yeah, they should have.
That's the standard.
but they're doing this on their server. I see.
Yeah, so the server should.
And then if you have duplicate host headers, I'm not sure what you should do, but probably not process it. I don't recall that part of the rest. So there's definitely something weird going on there. Anyway, so what happens now is AWS is going to serve from the attacker's bucket, could be some malware. And if this is cacheable, Akamai is going to think that it was the content for the legit endpoint. So we just cache malware on top of normal bank resources. So from that point on, anybody accessing the bank, they get malware. Problem, obviously, big problems. So you'll see a lot of parallels to the previous attack. It happened because of an interaction between different parties. They both did bad things that contributed to the final attack. Nobody's wrong, nobody's to blame on their own, but nobody's exactly right either. And then in the previous case, it was about a disagreement about the URL or the path, and now it's about a disagreement about the host header field. So this is still about some discrepancy. Are we good? Yes.
So a tiny question. In the bad request that you showed us, after input sanitization, you have two host fields.
Yes.
What happens there? Which one wins? The first that is in the error?
Yeah, so that's the part I was not prepared for. So in this case, AWS honored the first one, but I don't recall what the specification says.
Okay.
When you have duplicates.
But
That part I didn't do my
basically,
homework. I don't
you're
remember.
duplicating a header at the point at that point you don't know what happens because they should not be duplicated either, right?
Yes, I think so. Like I said, I don't know I don't remember what the RFC says now.
That's okay.
But, so what are we doing in terms of time? Maybe I can very, very quickly show you a third thing, but I'll not accept questions for this one because I'm running out of time. And if you saw frame shifters, you know what this is about. You have
AWS did also should not accept the questions.
What's that?
AWS also should not accept it.
Yeah, all of these things are, like I said, public, by the way, and they have been resolved. That's why I'm showing you here to this audience. You can exploit them. At least the instances that I showed you. Yeah, so maybe this worth pointing out, right? So again, I told you I would show you very specific attacks, which I did, but there are ways to generalize from them. So there are so many different ways to do web cache poisoning and web cache deception using different payloads. I'm showing you just one very specific instance of it. Right. And then the final one. So this is the one that the conference reviewer didn't think is a real attack. So in HTTP, you need to, there's nothing normally, so let's put it that way. So it is very easy to parse for an HTTP server the headers, right? Because there's this, neat line terminator at the end of every header. So you just parse until you hit this. But what about the body? Body is just raw bytes. So you need to have something else that tells the server where the body starts and ends, the length, the size of the body. So in HTTP 1.1, there's two ways to do that. One is by using this content length header. You say content length 16 and you send 16 bytes. And the other one is using a chunked body encoding. You indicate that to the server by including this header. Transfer encoding chunk counts as a package. If it has a different value than chunked, it means something different, not important for us. And then the body looks like this. It's going to go in chunks, where every chunk is 2 lines, basically. It is a length and then that many bytes. 6 bytes, you send 6 bytes. 8 or 10 hexadecimal, 10 bytes, you send 10 bytes. And at the end, you send a blank, empty, terminating chunk to indicate end of transmission. Okay? So these two ways are available to you. Clients are free to use whatever they want. Servers need to support both of them. What happens if you send both of these things together? That's the problem. Well, I mean, this thing alone is an attack in some cases, but I'm going to show you a more specific case where we don't need to make any assumptions about server behavior, at least in terms of process. Now, the RFC is usually very vague on a lot of different things, but not here. RFC says a sender must not do this. And must is very strong. You rarely see that in RFCs, so that's great. They tell you exactly what not to do, but it's about the sender, and the sender isn't required to read this. And if you're the attacker, you can send anything. Well, good news, the RFC also says something about proxy and server behavior, and it says that if you see both of these things, ignore content length. You must honor transfer encoding at chunks. So that's great. But we are going to trick servers into not doing that. That's going to be the attack. Here's the attack. The attacker sent this to the bank, right? So the attacker includes both of these headers, as promised, and then we do this little trick. We say not chunked, but semicolon chunked, right? That's going to be the trick in this instance. The proxy sees this. The proxy maybe has a very strictly written parser. It looks at this, it says, I don't know what semicolon chunked is. I can't do anything with that header. Keep it intact, under content length. Read 32 bytes, all of this, forward all of it. Right? But maybe the origin server has a more lenient parser. It could be a bug, or it could be just a feature. Maybe they want their parser to be a fuzzy match. And it looks at semicolon chunked and says, good enough. This is chunked for me. And then it follows the RFC and says, I have content length and transfer encoding. So the RFC says I must follow transfer encoding. So it does that. It parses the exact same body according to the other way to encode body. So that means this is the end of this request. And everything else is going to just remain sitting in the TCP buffer of the server. It's not discarded. Why not? Because this connection here is going to be a persistent connection. That's how most of proxies work. You just multiplex different clients over the same pecan in the backend, because otherwise you lose a lot of performance for no reason. So that's a precondition, just to be clear, but it's also a foregone conclusion. You always get that.
It works only with HTTP 1.1 also the more.
This only works with HTTP 1.1, exactly.
And all the.
So HTTP 2 solves this problem because it is a different way to encode frames and length. It's baked into the protocol. But HTTP 1.1 is enabled everywhere, right? Even if the preferred thing for between the browser and the service H2 or H3, you can still do this. With HTTP 2, there are different ways to code this attack, by the way. That was the previous topic that I mentioned. Anyway, so this is sitting in the buffer. So the next person, just some innocent person trying to access the same application, sends a brand new request for a legit endpoint or legit resource. This thing is going to get appended at the end of the byte sitting in the buffer. Now, the web server can finally see a complete request, but it's not what the user expected. So they get served a picture. So what's the impact? It could be a wide variety of things depending on the origin application's logic. There are ways to get really creative with this. But the base case, building on what we saw, if this is cacheable, you just cached a picture on top of a legit JavaScript. So the bank is broken now, right? So denial of service. Okay. Yeah, so again, a very similar pattern. Multiple things interacting and doing something unexpected due to that interaction. And now there's still a confusion, a discrepancy. It's about the length of the body. So now we have URI confusion, host confusion, and body length confusion. Three things. Right, so different mechanisms, but a lot of commonalities. So yeah, we tested this. Again, you may say a lot of assumptions there. So tested, we use fuzzing. So for the students here, this is how we do fuzzing in industry. It's a lot more. Yeah,
VR goggles?
exactly. We are goggles and everything. We always have smiles on our faces. Right. I don't know where I found this picture, but yeah, it cracks me up. Yeah, so we tested it. 3 papers, these 2, and then the frame shifter paper Engin presented in October. And basically, again, I showed you a very specific example with that semicolon trick, but turns out, you combine any one of these technologies with any one of those technologies, and if you see a shape there are ways to exploit that. And this is only one picture from one paper. So we have hundreds more of this. So tons of opportunities to exploit this. It happens all the time. Top vulnerability in HackerOne, if you look at it, just 70 or so bugs were submitted on the day, again, I received that review that claims this is not a real attack. So yeah, who knows? All right, so keeping that teaser.
When you submit next time, they say, oh, it's well-known attack.
Yeah.
All right.
You see that.
So that's my secret agenda, right? So if you get to review my papers, now you know. Now you know. Right. So why do these discrepancies happen? Almost at time. Yes. Why do these happen? Well, we saw various reasons due to parser bugs and sometimes features. Right? They're not compliant with RFC, but they're there for a valid reason. Make our lives easier. And these were mostly the examples I showed you because they are easy to understand. But these also happen due to RFC ambiguities, right? So you look at the specification of RFC, there's going to be some musts and shoulds and mays, and every time you see that's not a must, it's out to interpretation in one way or another. And so sometimes you may have an identical parser, you parse the exact same value, but you interpret that in completely different ways that leads to the same sort of problem. And then finally, so some of these standards were designed before proxies were common. So some of the things that are designed well according to theory on paper actually don't work. Like pipelining, so this is the teaser that I skipped, so not going to discuss that further. And then, like I said, today we have these three that cover all of the known attacks, but tomorrow we may discover a fourth field that causes the simulation. Yeah. All right, so going back to this picture, you get an attack like this, who do you sue?
Everyone.
Yeah, everyone. It's a lot of money though, right? So that's the thing. Is it a specific party? Is it everyone? Is it nobody? Well, the thing to, again, appreciate here is, this is not like your normal web application attack. This is not SQL injection. This is not XSS. Those are point vulnerabilities that you can fix with point defenses. You deploy a web application firewall that solves your XSS problem. This is a bit different. And I'm going to go back and explain why that's different, but also appreciate that this happens because multiple parties interact and disagree with each other. But this picture is very simplified. In reality, it may look more like this or like this. And then you have any two boxes on that picture that disagree on something, you may have a problem. So the scale is ginormous. And this is going to be a problem. So this same sort of problem is actually seen and appreciated, recognized, and solved to some extent by a completely different, research community, it's safety engineering community. So quick word on that. So safety people are interested in preventing accidents. It applies to technology as well. A good example would be all your site reliability engineering faults, right? There's a data center for a cloud infrastructure. You don't want the data center to go down. So this is not about attack, this is about accidents. And then this is a much older industry, of course. They've been dealing with building airplanes, building bridges so that it doesn't collapse, any manufacturing plant, any, nuclear reactors so that they don't melt down. So they have a very wide coverage, okay? And then they have been around for much longer than computers, of course. And so they do a lot of accident modeling and accident analysis, and they failed a lot and they learned lessons from that. And then today, their approach to safety has changed a lot. When I say today, that happened over the past 2-3 decades, so it's not very new either. So very quick summary of what they found out, thanks to their failures. They now know that reliability does not equal safety. Reliability is the rate of your individual components failing. Okay? So they figure out that you can have a genetically engineered development team that never makes any mistakes and then build bulletproof components for your airplane. That plane may still fall out of the sky. It's not about component reliability, it's about how they interact. And then they found out based on that systemic factors are important and root cause analysis is nonsense. Accidents don't happen due to a causal linear chain of events, X leads to Y, Y leads to Z. It's not like that. There are many things going on all at the same time, interacting in unexpected ways, and the airplane falls. Right? And then you see root cause analysis in a site reliability engineering team in your interviews, they're going to laugh you out of the interview room, right? It's a career-ending word, and yet Next to that SRE team, there's going to be a security team that asks for root cause analysis reports. So that lack of alignment, that misalignment between two very adjacent teams is baffling to me.
Can't the root cause be caused by a systemic problem?
So I mean, it's a very long discussion, but it's usually not a single thing you can rule out. Or if you attempt to do that, you remove that. Other factors find different ways to interact and cause the same issue. So it doesn't solve your problem. And so based on all of this, they said, can we do divide and conquer when designing and analyzing systems to solve our complex problems? And they decided that not really. So we should do that. Sure, but then you need to put together the entire system and analyze it as a whole, because there are some properties that only emerge when you look at the big picture. And those are called emergent properties, aptly named, and safety happens to be an emergent property. So you do divide and conquer, but you need to analyze the whole thing again. So here's the thing. All of this 100% applies to all the attacks that I showed you and some other stuff I didn't show you. And yet the security community is for the first time approaching, they are required to approach system security from this perspective. Right? It was always about in web security, securing individual things. Input validation, output sanitization, done. That solved 99% of the problems. Now it's different, it's not about that. And all of these attacks, all the attacks I showed you are like this. And so that's why this is going to keep happening. We find one specific thing that leads to an attack, we patch it, but there's a million different things that can lead to disagreements and cause the same problems again and again. We don't know how to detect for these things. We don't know how to measure these things. We don't know how to defend against these things because there's no distributed program analysis technique in existence that can analyze that whole distributed platform owned by different parties and developed by completely different teams. It simply doesn't exist. We need to invent it from scratch. Open research problem for everybody. Okay? And then that's exactly why companies are going to get blamed even though they play no part, because you look at that big picture, well, if you can analyze it, you know exactly who is to blame maybe or what factors contributed to that. But from an external researcher's vantage point, you have no idea. You interact with the front end, something really complex happens in the back end, you have no idea what broke why. So you can only make an educated guess, which can sometimes fail. So they are not necessarily at fault. It's just that the problem is not very easy to pick apart from an external vantage point. And then finally, why does this happen? Like I said, we don't know how to solve this problem. There's a grand total of 0 security defense related papers on these topics. There is a lot of attack papers now, or measurement papers. We wrote half of them. So it is really new to the academic community as well, but it has been here for, like I said, precisely 1 decade for the CDN folks and for proxy vendors. So it is big. There's a lot of opportunity to write new papers on this. Come join me and we'll do it. Okay, so I'm actually 2 minutes past time. I appreciate all the questions. I was going to feed you with one more potential defense, but I'm not going to waste any more of your time. So I'll stop here. Thank you for watching.